So as we saw last time, we have this concept of momentum, which is the quantity of motion, deals with the mass and velocity. And we also have this new idea of the change in the momentum. And so here's how we consider it. Let's, for example, take a bowling ball. Many of you have been bowling. So here's you and you're bowling. And when you're holding the bowling ball back here it's not moving, and then sometime later, here's the bowling ball and it's moving down the lane. So over here, it wasn't moving, so no momentum. Here it has some momentum. How did you change its momentum? Well, basically, you took its mass and you changed its velocity. But how did you do that? Well, you had to apply a force, and that force had to last for some time. And so this is our idea, that if you take an object of a certain mass, you apply a force, the force lasts for some time, you can change the velocity of an object. That's actually not that crazy of a concept. We've been talking about that for a couple weeks now, a couple months, in terms of, normally we talk about it in terms of acceleration. We say, oh, well, the acceleration is the force divided by the mass. That's Newton's second law. But as we saw, acceleration is also the change in velocity divided by the time that the velocity is changing. And we can see that this has the same structure of this. This concept here is called the impulse. Literally, the impulse is the force times the time that the force is applied. That is the impulse. And so when you talk about the impulse on an object, this is one way to calculate it. Coincidentally, by the way, in French, impulse, basically, I don't speak French, but it starts with a P. That's why we use this idea that P is the letter we use for momentum. So when you look at this here, well, this is the impulse, but this right here is also, this is the change in momentum, because the mass times change in velocity is the change in momentum. So we use these interchangeably, even though they're not exactly interchangeable. Sometimes we say that the impulse is the mass times the change in velocity, and sometimes we say, well, the impulse is just the change in the momentum. So we use this word impulse to denote all three of these, but really it's just this one, but sometimes you can calculate it the other ways. So that's the impulse. Now, how did we talk about it? Well, one of the things we talked about was the fact that there's a relationship here between the stopping time and the stopping force. And so if we use this example here, I'll give you another obvious example. All right, so here's your intrepid physics student. I'm going to climb up to the top of the high dive. Now, you get up there and you got to jump, and there's two ways to jump. You can obviously just jump into the water, no big deal. And if you jump into the water, you're going to come to a stop. The water's going to splash a little bit, and you're going to come to a stop. You're going to come to a stop somehow underneath the water somewhere, right? Yeah, you came to a stop. So in this case, you have your mass, and right before you hit the water, you were moving, and then you came to a stop. So you have your mass times your change in velocity. And this velocity is, your initial velocity is right as you hit the water, and your final velocity is when you stop. You could do that, or you get scared and you freak out and you could jump onto the concrete. Now, I don't suggest this, because if you jump onto the concrete, something bad is going to happen. You are still going to come to a stop. Your final velocity is still 0. Your initial velocity was still the same, just as it was this one, and you came to a stop. But why are these two different? Well, in this one over here, it took a long time, comparatively, to come to a stop. So this one here, you have a small force because your stopping time is comparatively long. So you still have the same mass and the same change in velocity, but over here, what's the difference? You came to a stop in a very short period of time, so because your time was very small, that means the force was very big. And this, by jumping into the water, you increase the stopping time. Which decreased the stopping force. That phrasing is the phrasing that I want you guys to be able to use. And this is really useful. Think about why things are soft in general, why anything is soft. Well, for the most part, like you could make your bed out of concrete, you could make your pillow out of concrete, but when you jump on it, you want it to be soft because you want to increase the stopping time, which decreases the stopping force. That's why things are soft. I know in, let's say, boxing, for example, those boxing gloves are really padded. Well, why are they padded? Well, they're padded because in bare knuckle boxing, you're going to break your hand. Because if you hit somebody, it's going to be a small stopping time and a large stopping force. You'd apply a large force on them, but they also apply a large force on you. So this is one way that we can decrease the force on somebody. What's another way we can decrease the force as a concept? Well, if we go back and we look at this general form right here, the force is inversely related to the time. So as time goes up, force goes down. They're on the same side of the equation, and they're both on the top. So one goes up, the other has to go down. But if you look over here, if you wanted to decrease the force, you could actually decrease the change in velocity. So let's use a skydiver. Let's use a skydiver as our example here. When you jump out of an airplane, and we talked about this before, if you jump out of an airplane, you start falling, and eventually the force down from the earth balances out the force up from the air. So you're falling at a constant speed, but this is like 120 miles per hour. Like you're falling really fast. And if you don't open your parachute, you're going to hit the ground and you're going to splat. This is not a good look on you. Okay? You're going to splat. And basically what happened was you changed your velocity. Your initial velocity was about 120. Your final velocity was 0. So you had a large change in velocity, which means it's going to lead to a large force. But if along the way you're smart enough to pull your parachute, so you pull your parachute and you're like, oh, I love this, right? Okay. So here's your parachute. There's your parachute. Your parachute, when you pull it, it slows you down from about 120 down to 20 miles per hour. And so now when you land so softly, comparatively, and everybody's a winner. So here, your change in velocity, your initial velocity was 20, your final velocity was 0. And we can see that this is a much smaller change in velocity. So for this one, we can see you have a large change in velocity, which gives you a large force on you. Over here, because you have a small change in velocity, you get a small force on you. That's why it's nice to slow down. Okay? That's why it's nice to slow down. So the change in velocity can make a big difference. One other thing that I want to mention is that this force that we're implying, this force here, is the They call it the average net force. And basically the average net force is the unbalanced force on the object. If there's only one force, then it's that force. And we're going to imply that our force never changes. It's a constant force, so we don't need an average. But if this force were changing, we'd have to take the average force. But we don't need that here. Another great example of this, okay? Another great example of this, let me get rid of these guys. Is I don't love ballistics, but you can talk about, let's say, a handgun versus a rifle, for example. So one of the things that you may or may not know, and it's not super important to know, but I'll describe it for you anyway, is let's say you have a handgun. So here's your handgun. Okay, and there's your trigger right there. And over here you're going to have a rifle. So now, in a handgun and a rifle, you can actually put the same bullet in a handgun and rifle as long as it has the same diameter of bullet. And as you shoot the bullet out of here, and you shoot this bullet out of here, which do you think is faster? Well, it turns out that this is much, 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 much faster. And there's a reason that it's much faster. So, because it's the same bullet, right, all the explosion that happens in here is encased in the bullet. The only thing the gun does is just make it explode. So this bullet comes out here, this one's going much slower, this one's going much faster. Why is that the case? Well, if you look over here, you have a certain amount of force, you have a certain amount of mass. Same thing over here, you have the same force, and you have the same mass. Okay? But what happens with a gun is the bullet explodes here, and there's this explosion that happens behind it. And this exploding gas pushes the bullet out. Same thing here. This exploding gas pushes the bullet out. But because this is so much bigger distance, the time that the explosion pushes on it is much bigger. And since you have a longer time, you have a larger change in velocity. This one is a smaller time, so you end up with a smaller change in velocity. Again, if the force and mass are the same, the velocity is determined by the time that the force is applied. That's just another kind of random example. Another example that I want you guys to be familiar with, let me get rid of this one, is this example of a ball hitting a wall. So this is kind of interesting. So let's talk about a tennis ball. Okay? Or it could be a golf ball or a baseball or any kind of ball. Okay? Maybe we'll go with baseball because they're easy to draw. So here's your wall here. And what I'm going to do is I'm going to throw my baseball in. And my baseball is coming in this way, and it's going to hit this wall here, and then it's going to come out this direction. So it's going to rebound off the wall. Now it's going this way. And I'm going to tell you that the mass of a baseball, okay, the baseball has a mass of 0.140 kilograms. That's the mass of the baseball. And you threw it in, and it was going at, let's say, 20 meters per second on the way in, and on the way out, it's going at 10 meters per second. These are the speeds. I want to know if we can find how much force the wall exerted on the ball. Okay? Well, there's a couple things we need to know. If we think about this equation here, We know the force times the time that it's applied. We know that's one way to find the change in momentum of the ball. Another way to find the change in momentum of the ball is if you take the mass times the change in velocity of the ball. That's another way to find the momentum. So what can we figure out we have here? Well, we have the mass. Can we figure out the change in velocity? Probably, so we're going to use this to find the change in momentum. And once we know that, if we want to find the force, we're still going to need the time that's here. So let's wait on that though, because the interesting part about this is here. If I want to find the change in momentum is equal to the mass times the change in velocity. Well, change in velocity, the change is always the final value minus the initial value. That's how we define change. That's how we define change anywhere, but that's how we define change in this context. So let's see if we can't figure out what these values are. So the change in momentum, we know the mass is 0.140. And then what is the change in velocity here? Now you're going to be tempted to think it's 10. Oh, it went from 20 down to 10, the change is 10. But I don't think it is, because these are the speeds, they're not the velocities. If you look at this one, which way is it moving? This one is moving to the right, so its velocity is positive 20. And this one's moving to the left, so its velocity is negative 10. So when I go to put this in here, this is actually negative 10 minus 20. If you think about the way this looks on a number line, this velocity is positive 20 here. Here's your 0, and your initial velocity was negative 10. What is the difference between these two? It's not just 10, the difference is 30. In this case, it's going to be negative 30. So, when we go to put this in, the change in momentum is equal to 0.140 times negative 30, and this is going to give me the change in momentum. I will calculate that for you. Hold on. So it turns out that that change in momentum is negative 4.2, and again that's kilograms meters per second. It's a silly unit, but that's what we have. Now, it's negative because it had a lot of positive momentum to begin with, and it has a lot of negative momentum. So it's a large negative change in momentum. So now we have the change in momentum. That's cool. If we're going to figure out how much force, we're going to need to know the time, because we have the change in momentum. We're going to need the time, and then we can find the force. So let's say it's in contact with the wall for 0.1 seconds. It's a tenth of a second. No problem. I can go back to this equation and say that the force times the time that the force is applied is equal to the change in momentum. We know the change in momentum is negative 4.2. I told you a moment ago the time was 0.1. I can calculate the force directly. Force is equal to negative 42 newtons. Now what does that mean? That means that when the ball was in contact with the wall was applying a force of 42 newtons, and it lasted for a tenth of a second. Why is it negative? Well, because the wall was pushing it to the left, and so we end up with this. So this is the force of the wall on ball. The follow-up question is, if the wall exerts negative 42 newtons of force on the ball, how much does the ball exert on the wall? And the answer to that is positive 42 newtons, because the ball pushes the wall to the right, and these are Newton's third law force pairs, equal in strength, opposite in direction, act on the other object. And we can see that we have this idea here that they exert equal forces but in opposite directions. That wraps up our momentum and impulse discussion.